Hello my friends, welcome to my channel. In this video, we are going to see how we can calculate a differential equation using numerical method. And the method that I'm going to explain in this video is finite difference method. For that, I just choose the very simple differential equation. And I will show how we can solve it numerically and how we can solve it analytically. So here you see, let me choose the laser pointer to be a little clear. Okay, here you see a very simple differential equation, and we know that it has very simple analytical solution. If we multiply the both sides of equation with dt and divided it with n, we will have dn over n equal to minus a dt. In this equation, a is a constant, and if we take the integral from both sides, from n0 to n and from 0 to t, and we know that the answer of this integral and the solution of this integral is simply ln of n from the lower limit to the upper limit, from lower limit n0 to the upper limit n, it's equal to minus a t. And if we substitute the n0 and n, we will have ln of n minus ln of n node equal to minus at, and we know that we can write the left hand with the ln of n over n node, and it will be equal to minus at. And if we take the exponential from both sides of this equation, we will have n over n node equal to e minus at. And if I multiply both sides with n node, we will end with this simple equation. So we see that the analytical solution of such a differential equation is just a very simple function, n equal to n node multiple to exponential of minus at. So I want at this point to plot this function and to see how does it behave, although we see that it's just an exponential decay. But because I want to also calculate numerically this differential equation, and I will use MATLAB for calculation it numerically, so I want to plot both analytical and numerical solution and compare them. So I end it here. Let's plot it in MATLAB, but you can do it in any software that you are familiar with it. No matter, here I have MATLAB. Okay, I have MATLAB. I create new file. So I want to just plot this function in MATLAB at different times. So CLC, maybe you know that CLC, just clear the command window and clear here, just clear the cache of MATLAB and close all, will close any open figure. So close all, I write here close all. So I should mention here that n0 here indeed, if we imagine that time is t, so n0 here is the initial condition. Imagine that when t is equal to 0, n will be equal to n0, and this n0 it's a known value and it's known as the initial condition. But if we imagine that here t is not time, this is the coordinate, so here n0 will be the boundary condition. We know that any differential equation has the large number of solutions, but what limits it and what gives us the non-trivial solution is boundary condition and the initial condition. So here is we imagine that time is 0 and n0 should be the initial condition, and it has a known value. So I put n0 here equal to 1. Okay, 1. Then also a is a constant. I put a is equal to 1 again. Then I want to plot it from t min, minimum time, that I put it 0, to maximum time, t max. I want to plot it from 0 to 10. And I want to define the number of plot. I mean, I want to plot it with nt, in nt number, and I define nt equal to 100, and if nt is the number of points that I'm going to plot the function at this point. So dt here, I define the time step with the, it should be 1 divided by number of points, and number of points is nt. So our time step here is 1 over nt, and nt is 100, so dt will be equal to 0.01. So I define t, I just define a linear matrix for t from t in with dt step to until t max, right? Okay, and what is my function? N is n naught multiple to exponential of minus a multiple to t, right? Then plot t n. Let's see. Let's first save the function. Where's the save? Home. I don't see the save. Where is it? Home. Okay, let's run. If I press F5, it will ask me saving. Analytical solution, right? Solution. Okay. I should put an underline here because there should not be space. When we save the file name, there should not be any space between the letters. So I just put an underline here. So it works. Okay, you see, here is as we predict here, n is just exponential decaying, and at the initial, at the 0 moment of time, that is initial value, the value of function is just 1 as we define here. So let me make it a little beautiful. Beautiful line widths. Line widths. I just make the figure a little thick. F5. You see, okay, and grid on. I add grid on my plot. Grid on. F5. Okay. So you see that we had a differential equation. We solve it analytically, and we get this function, and we plot this function. Now I want to explain how we can solve this differential equation using numerical method and using finite difference method, because all of the partial differential equation or differential equation has not analytical solution. So numerical solution could be a powerful method for calculating the partial differential equation. We will use the definition of the derivative for solving the partial differential equation or a differential equation numerical. We know that the definition of derivative of function with respect to t is just limit of nt plus delta t minus nt divided by t plus delta t minus t, and these two t will cancel out each other. So imagine that we have a function like this. It's just a random function. I choose this function, and if the value of function at time t equal to nt and the value of function at time t plus delta t equal to nt plus delta t, so the definition of derivative is just the slope of this function when delta t tends to 0. You see value of function at this point minus value of function at this point divided by t plus delta t time in this point, then minus t time at this point. These two t cancel each other, and we can approximate the definition of derivative with this function. But we should take into account that delta t here should be very small. It should be very close to 0. If here, you can imagine that here delta t tend to 0, so this point will move toward the time this point, right? And the value of function at this point also will move toward this point. So When delta t tend to 0, this green line will be tangent to this blue line, and this is just definition of derivative, and we know that the derivative of function at the time t will be just a tangent line to our function at that point. So if I use this definition for calculation of this differential equation, I just substitute the definition here, so, and I write the right part just here. So nt plus delta t minus nt divided by delta t will be equal to minus a nt. I did nothing, I just substitute this in this function. And if I keep this value at the left part and gather all the other part at the right hand, so we will have here minus a delta t nt, and if I bring this part to the right part, I will have plus nt, and after simplification I will end with this simple equation: nt plus delta t is equal to nt multiple to 1 minus a delta t. So we have this equation, and it says that if I want to calculate a function at any time, let's choose again laser pointer here, at any time t plus delta t, it will be the value of function at previous time step multiple to 1 minus a delta t. If I want to calculate it one step time further, I mean if I want to find the value of function at t plus delta t, it will be the value of function at the previous time step and t plus delta t multiple to 1 minus a delta t, right? And if I simplify it, and I know that the value of function at t plus delta t is just this one, I substitute this value here, I did nothing, and simplify it, nt plus 2 delta t will be equal to nt multiple to a 1 minus a delta t multiple to 1 minus a delta t, and finally nt plus 2 delta t will be the value of function at nt at the time t multiple to 1 minus a delta t squared. At the same way, I can show that the value of function at the time t plus m's delta t will be equal to the value of function at the time t multiple to 1 minus a delta t in the power of n. So if we have the initial value at the time t equal to 0, the value of function is n0, and this is the known value, and we know this. So the value of function at the very small time step after the initial time will be equal to n0 multiple to 1 minus a delta t. At the same way, the value of function at the m's delta t will be equal to the value of function at the initial point multiple to the 1 minus a delta t and power of n. Okay, so let's calculate this value of function just using MATLAB, because it's enough to put this function in a loop, and we know the initial condition, and calculate the value of function at very small time step after the initial value, and then calculate again the new value of function at the new time step. It's enough to put just inside a loop in MATLAB. So I'm going to the MATLAB again. I have here. So because I want to be the analytical and the numerical solution to be recognizable, I just define the numerical value with big N. So at the first point, okay, I define the number of time step for numerical calculation. So I just define it by floor function, floor of tmax minus tmin, right? Tmax minus tmin divided by dt, right? Let's check. I pressed F5. Something is wrong. Let's see. floor. What is the, I think floor should be like this. Yes, everything is right. Okay, so this is the indeed the number of step for time. We increase the time with this nt number, with nt number. So, and okay, then I just define n. I allocate memory for function n, zeros, 1, nt, right? Also, I allocate a function for time. I again define it with the capital T to be different from the analytical solution. Zeros, 1, nt, right? Let's check. Press the 5. Everything is okay. So I need to define a loop. So for every time step, I define an index I. So the I should be changed from 1 to capital NT, number of time step. And okay. And what is my function? My function is n, capital N. In time, in the time I plus 1. At the next time step, it means that my function at the next time step will equal to my function at the previous time step multiple to 1 minus a multiple to dt, right? And also I forget here to define the boundary condition, and here just multiple sign, and we know that our function at the initial time, at the 0 time, will be n1 equal to 1. The same value that we defined in analytical part with n node. This is the same. This is the initial condition. And we should take care that in MATLAB we cannot define 0 index for a matrix. So the 0 index, the 1 index here is correspond to the 0 time, right? Okay. So I should update also the time in every loop, and my time is increased just by step, and the number of steps is just, the amount of this step is just t, so it should be I multiple to dt, and here should be I. Okay. As I mentioned here, I represent I1 here represent the 0 time. I just write here to put it, to remember it. So I equal 1 represent the 0 time. Okay, so we have the value of function at the 0 time, right? And we start calculating it one dt step after 0 time. So in this loop, we calculate the function and update the function. So if I plot t capital N, and let's also Control C, Control V, make the line a little thick, and plot it another form with dashed line F5. There's an error, and what is this error here? Error says that vectors must be the same lengths. You see here, if we put I equal to NAT, the maximum value, the maximum index for capital N will be equal to NT plus 1, right? But the maximum value for this time, when we put I equal to NAT, will be equal to NT. So they are differ. The lengths of this two matrices are different to each other. We can see it from here, open variable. You see, this is entity. No, we should open the n. We should compare n, the capital N. You see, this is 1001. It has 1001 column. And what about t? It should be 1000. Just one column less than. Yeah, it's 1000. And this is 1001. So we say that I1 represents the 0 time. But here we have not 0 time. Right? Here when I equal to 1, it represents a time step after initial value. So I just manually define TT. I just manually add the 0 time to this time matrix. This matrix that represents the time. And I put 0 and T. What I did here, I just manually add the 0 time, that is 0, to this time matrix and define the new matrix with TT. And if I plot TT here, and with respect to TT, it should work. Let's see. Right. And here I have the numerical calculation. Let's add and hold on here. Hold on to have both numerical and analytical. So the solid blue line is analytical solution, and the dashed orange line is numerical solution. You see, they are fit to each other. So let's see what happens if we change the dt. We say that dt here that represents delta t, we say that it should be small, right? When nt is 100, so dt should be 0.01. So if I decrease this nt, also dt should increase. Let's calculate. I press F5 and update. You see, the numerical result are different than the analytical one. How much is dt? We can see here. dt here represents our delta t. This is 0.1. And if I increase dt more just by decreasing of nt, you see, there is not any agreement between the analytical and the numerical solution. And if we can also calculate the error calculation, and here I define the, let's plot it, new figure plot E, and make it a little thick again, Control V, F5. I didn't define the error here. Here, E error is just n minus capital N, and this is the absolute error. F. What's the rank here? Plot E. Line widths. What is the rank here? Let's see. If I remove it, this is a capital P. It should be small p. F5. You see, this is the absolute error. This is the absolute error. So if we increase the number of points, in other words, decrease the dt, here dt is 1. You see, dt is 1. dt is 1. If we increase nt 1, 2, 3, for example 1000, you see the maximum error is in the order of 2 multiple to 10 to minus 4. And you see maximum error is somewhere here. And this is obvious when we decrease the number. F5. You see the maximum error is here. Very large error. You see, this is really large error. So we see that when we applied when we use a small value for delta t, the numerical solution and the analytical solution has a good agreement to each other, and the error is very small. And as we increase this number in t and decrease in the time step, the error will decrease here, as you see here. Okay, I think that's it. I hope that you enjoyed my video, and if you like it, I will upload more video, and this video will be about numerical calculation, about the physics, about the mathematics, and at the next video I'm going to solve the other differential equation, a little complicated, and also I will make some video about the simulation with COMSOL and compare the COMSOL result with the MATLAB with the numerical result. So if you like these videos and you don't want to miss my next videos, please don't forget to subscribe my channel. Thank you very much.